Hi, I am Varun Joshi and welcome to day 30 of our Certified Kubernetes Administrator 2025 course. Today we'll be diving into encryption and TLS, transport layer security. Encryption is fundamental for securing data both at rest and in transit. And TLS is a crucial protocol for ensuring secure communication between clients and servers. So what we have on screen, encryption. Encryption is used to convert plain text into ciphertext. Firstly, I am not in line with the words that they have chosen, plain text and ciphertext, because plain text has text in it and encryption is not just used for text. It is used for images, videos, documents, essentially any data. So encryption is a method wherein you convert a humanly readable data into unreadable format. So anything unencrypted is plain text and anything that is encrypted is called ciphertext. But why do we need encryption to begin with? Now let's take example of Seema, who wants to log in into her bank, which is Pink Bank, and whenever she accesses pinkbank.com, she has to enter her credentials. If she enters her credentials in plain text, then any hacker that is sitting here can see that data over the internet, and that is not right. So we wanted that data to be in an unreadable format, hence we used encryption for this. And the example I just talked about is a way via which you can encrypt data that is in transit. In transit implies data that is going from one system to another. Then there is also encryption available for data at rest. Imagine your laptop. If your laptop has a drive and that drive is encrypted, God forbid if your laptop gets stolen, then the thief will not be able to see your data until and unless he or she provides a unique key or has the encryption, and we'll discuss these terms as we progress with this lecture. So encryption at large can be thought of as two types. First is symmetric encryption and then there is asymmetric encryption. Symmetric implies symmetry, so in that you only have a single key, and that single key is often called shared key. Now shared key is not the only term that you would see. Some call it secret key, session key, but in essence in symmetric encryption there is only one key that is used for encryption and decryption. Second is requires secure key sharing. For example, if let's say Seema encrypts something with a single key, then how will pinkbank.com decrypt that data? Because as we understand, same key is used for encryption and decryption, and if Seema chooses to share that key over the internet, then there is a possibility that someone could intercept that traffic. Hence it is imperative that we find means via which symmetric key can be exchanged between two systems securely, and we'll see how that works later in this lesson. Symmetric encryption is fast and used for bulk data. Key compromise breaks security, and that's true. If the key that is used to encrypt data is compromised, then that hacker or that malicious user can decrypt your data. Example algorithms. AES stands for Advanced Encryption Standard, and this is the standard that is widely used with symmetric encryption, and this is available in various bits. You have 128-bit encryption, 192-bit and 256-bit. 256-bit is the most secure, and you would see all the cloud providers that are providing symmetric encryption are using AES 256-bit behind the scenes to encrypt your data at rest. There is Chacha 20, and this is used in Android and mobile security. Then there is Blowfish, Tofish, and DES, which are now legacy. At large, being a DevOps engineer and a cloud engineer, you would often see AES in your daily operations. What are the use cases? Secure data transfer. In parentheses, I have written post TLS handshake. You remember here I said that if SEMA has encrypted something, and Pink Bank will not be able to decrypt that unless Pink Bank has the key that was used for encryption, and sending that key over the internet is insecure. Then how do we send that key? We send that key using a combination of symmetric and asymmetric encryption, and we'll be looking into that in detail later in this course. So secure data transfer post TLS handshake. So once the TLS handshake is done, then symmetric key is used to encrypt data when two remote systems are talking to each other, especially over the internet, and we'll see this in a little while. Disk and storage encryption. So if I talk about cloud providers, your EBS, EFS in AWS, or Azure Disk in Azure, all of these are using symmetric encryption behind the scenes, and the key management is done via their native key management software. For example, AWS is using AWS KMS, Azure is using Key Vault. So all these cloud providers are using symmetric encryption to encrypt your file, object, and block storages. Encrypted backups and snapshots. These things also use symmetric encryption. Database encryption also uses symmetric encryption. So I hope symmetric encryption is understood. Now let's move to asymmetric encryption. Asymmetric encryption is also called public key cryptography. And here you have two keys, a public key and a private key. As the name implies, public key can be shared with anyone, and private key is supposed to be secret. It should only be with you or the person who is generating a key pair. Slower and used for key exchange. So we said that symmetric encryption was fast, and that is why it was used to encrypt large chunk of data. Here we are encrypting databases, old disks, and these disks can be of multiple TBs, and we used symmetric encryption for that because symmetric encryption is fast, and here asymmetric encryption is slow. So asymmetric encryption is typically used for key exchange, and once the key exchange is done, then the data is encrypted using symmetric key. And if you are not able to connect the dots right now, do not worry, because we are going to dissect all things encryption step by step in this lecture. What are the examples of asymmetric encryption? ED25519, this is the modern default for SSH keys and JWT signing. JWT is JSON Web Token. Previously RSA was widely used, but now ED25519 has replaced that. ECC is also used. What are the use cases for asymmetric encryption? First is, as a DevOps engineer, you would be often using SSH to log in into your Linux boxes, and that uses asymmetric encryption behind the scenes because you always deal with private and public keys there. Then there is TLS handshake, which we'll discuss in detail later in this lecture. So now that we understand both symmetric and asymmetric encryption, it is good time to introduce what are the approaches when it comes to encryption. We discussed briefly that there is data that is in transit, and then there is data that is resting. So in transit protects data while it is moving between client and server. So if you are interacting with github.com, for example, then the data that is being exchanged between these systems is called in-transit data. Pod to pod communication. So we also want to take care about the encryption when we are dealing with pod to pod communication, and that is also called in-transit. And I want you to understand that by default, when one pod is communicating with another pod, then that data that is being sent and received between two pods is not encrypted by default, and you can encrypt that by using something called a service mesh. And service mesh usually has something called MTLS, mutual TLS, which is used to encrypt in-transit data between pods. Then there is Kubernetes components. Now components like kubelet, kube API server, etcd, anything that communicates with each other in the Kubernetes cluster, especially your control plane and data plane components, they use in-transit encryption, and that encryption is provided by TLS, and we'll be looking into this in detail when we move to our next lecture, where we will be discussing TLS in Kubernetes. How is it implemented? TLS is most commonly used protocols. So whenever you are accessing a website, then TLS is working behind the scenes to provide authentication and encryption. Kubernetes components like kubelet, API server, etcd use TLS extensively, and we'll see this in the next lecture in detail. MTLS is used by service meshes like Istio. Like I said, by default, pod to pod communication is not encrypted, but if you want that encrypted, you can use something like MTLS. Then you can use service meshes like Istio, which allow you to have MTLS when pods are communicating with each other. Then there is at-rest encryption. At-rest encryption is encrypting the data that is resting. So if it could be encrypting your block storage, your file storage, your object storage. This protects data when it is stored in persistent volumes in Kubernetes databases, etcd, Kubernetes backing data store. So if I talk about cloud providers, then etcd is encrypted by default using symmetric encryption. However, if you have an on-premises deployment, then you will have to find ways via which you can encrypt your etcd, and etcd must be encrypted because all data related to your Kubernetes cluster is stored in etcd. How is it implemented? Symmetric encryption, as we have seen before, encryption at rest is typically achieved using symmetric encryption, and in-transit encryption is typically achieved by using TLS. And here we have said that symmetric encryption usually uses AES 256-bit, which is the highest, and then Kubernetes encryption at rest encrypts resources like secrets, persistent volumes, etc. So in summary, when we deal about encryption, then encryption we talk about basically two things: in transit and rest, and both of these are very important when you are dealing with a production grade implementation, because you would want to ensure that you have both in transit encryption for data that is being transferred between two systems, and then you also want encryption at rest so that the data that is resting in your block storage, object storage, or file storage is encrypted properly. Now that we have an understanding of encryption and the encryption types and different approaches of encryption, I want to discuss 4 scenarios with you, and these 4 scenarios will solidify your knowledge of encryption. Scenario 1 is symmetric encryption. So what we have here is we have our user Seema. Our Seema user has a laptop, and her laptop is encrypted using a symmetric key. Not her laptop, the hard disk in her laptop is encrypted using this symmetric key. This is fine. Now what happens is, let's assume that this is a Windows laptop that uses BitLocker for encryption. So whenever you have BitLocker installed, then what would happen is whenever Seema wants to log in, she'll first have to enter a BitLocker pin, and once she enters that pin, she'll have to enter her login credentials, and then she can continue to do her work. If her laptop gets stolen, for example, then the person who has stolen it will not be able to see any data inside her laptop until and unless they have the key or the BitLocker pin. Even if they detach the hard drive and plug it into another laptop, they will still not able to see the data because they do not have the symmetric key. All they will see is gibberish encrypted data. This is how symmetric encryption helps with data at rest. Then scenario 2 is credentials encryption. So let's say now Seema wants to access pinkbank.com. She has her credentials and she has encrypted her credentials with a symmetric key. If she sends the login details encrypted to the other side, to Pinkbank, then Pinkbank will not be able to decrypt it because Pinkbank does not have the symmetric key that was used to encrypt this data. And Seema, on the other hand, cannot send this symmetric key securely to the other side, because if she sends the symmetric key, the encryption key, then a hacker could intercept the traffic, and once the hacker knows the symmetric key, and when Seema is sending her bank login details, the hacker can see the bank login details because the hacker has the symmetric key that was used to encrypt the credentials. Hence, we must find a way to securely send this symmetric key to the other side, and here we use a combination of symmetric encryption and asymmetric encryption, and we are in scenario 2 right now. Once we move to scenario 4, we'll dissect this bit by bit. So let's move to scenario 3. Scenario 3, we will talk about asymmetric encryption, and as DevOps engineers, you would be using SSH all the time to log in into your Linux boxes. So what we have on screen is we have AWS cloud, and in AWS we have spun an Ubuntu VM. We have our beloved internet here. Then there is a sweet hacker that is waiting for decrypted data so that he can create a havoc. Then we have Seema here. Seema is our happy user who wants to log in into her Ubuntu VM. So what Seema will do is Seema will generate a key pair, and you can use a utility like SSH keygen to generate a key pair. And once this key pair is generated, Seema will be copying the public key onto this Ubuntu VM so that when she logs in, she can get into the system. But public key is placed here and private key remains with Seema. Understand that private key is a secret that will always stay with Seema. Private key won't go here, there or anywhere. It is supposed to stay with Seema. So let's go to the terminal, and I want to show you the process of generating this key. It's very simple. I'll just write SSH keygen, and there are few more options that you can see using -h, but I'll just write SSH keygen. I'll press enter. It says that we'll generate a public private key pair using ED25519, which is the default. If you look at -h, you can even generate RSA keys. So I'll press enter. It says, do you want a passphrase? I don't want a passphrase. I'll press enter again, and it says the key is generated. If I hit ls and press enter, ls-lthr, oh, the key is generated in this path. So let me go here. I'll copy this. I'll cd here ls. I see that this key is generated here. You see, if I hit ls-lthr, I will see that here is the file that was generated on 1st of May, and I see two files here. There is a public key which has a .pub extension. When we are dealing with TLS, this could have CRT extension as well. And if you go to GitHub notes, then you would see I have defined all the popular extensions that you would see with public and private key files, and just go through this entire GitHub notes. This holds key information for your learning. Now let's go back to our terminal, and we see here both these are generated. And let's do one more thing. I don't want an unnamed key, the default name. I don't want the default name. Let's go back. Let's go to CD courses CKA, and that's day 30, and then I will again run SSH keygen, and then I'll call this my key. I am just writing my key here. So what will happen is this my key will be created in day 30 itself. Previously I pressed enter and it was created in the default location. If I do not provide an absolute path here, if I just write my key, it will create it in the present working directory. I'll press enter, I'll again press enter, again press enter, and if I do ls, I see both my keys, the public key and the private key, are created in day 30. I want you to understand one thing. I am using this repository for my course, and by mistake, if I commit these keys onto my GitHub repository, this will stay there. Even if I delete it, even if you check commit history, you will see that there were keys that were committed. Never commit that mistake. So if I go here, you always have an option to create a git ignore file. So what I've done is I've created a git ignore file that will prohibit these extensions to be committed into my GitHub repository. But if you see here, my private key does not have an extension. So be extremely careful when you are dealing with keys. Do not generate these keys into a directory that is tracked by your Git. So what I'll now do is I will go to my diagrams again. Now you know how to generate a public private key, and then I'll go to diagrams again. In the diagram, I have pasted the public key here and the private key is with Sima. So how does SSH authentication work? So what happens is, you would be thinking that whenever Sima tries to SSH into Ubuntu box, the private key would be shared. Private key never moves, it stays with Sima. So what happens is, when Sima tries to initiate a connection, this server sends a challenge to Sima, and that challenge is just a random text. And once Sima receives it, Sima must sign that challenge with her private key. Understand, Sima is not sharing her private key. Sima is just signing the challenge with her private key. And once she signs that challenge and sends it back to this server can then verify that indeed that challenge was signed by Sima's private key using the public key. So I'll repeat the process again. This server sends a challenge, Sima signs that challenge with her private key and sends that challenge back. And once that challenge is sent, since this server already has the public key of Sima, and how does it have it? Because we copied that in step 2 and we copied it into this path. This is the default path where your public keys will be stored, and this path you see a tilde here, this denotes we are copying it to the home directory of the user. And once this Ubuntu VM has the challenge signed with the private key, it can use Sima's public key to verify that it was indeed signed by Sima. Any other public key will not work. Only the public key that is associated with this private key can verify that it was indeed signed by Sima. And once this verification happens and this server verifies that it is indeed Sima who is trying to log in, I will allow her to SSH into me. And that is how SSH authentication works. It is imperative to understand that this key is not leaving, it is just signing the request. And the public key cryptography is based on these two facts. So if I move to my GitHub repo, you see both of these points I mentioned somewhere. Yeah, if a message is encrypted with Seema's public key, only her private key can decrypt it. This holds true for public key cryptography, not just Seema's example here. If something is signed with her private key, like this challenge was signed by Seema's private key, anyone with the public key can verify that it came from her. So this public key is the one that is associated with this private key. So I hope you are now able to connect the dots, and the whole process that I just discussed is available in the GitHub notes. Once you watch the video, I encourage you to go through the GitHub notes. I'll go back here and let's move to scenario 4. That is the most important for you to understand, and that is how TLS works. So before we start anything, previously we had HTTP, just HTTP, it was unencrypted. Then HTTPS was introduced. HTTPS is Hypertext Transfer Protocol Secure. It provided security. Previously, SSL was used for encrypting HTTP traffic, but now TLS is used to encrypt HTTP traffic. So you will still hear people say this is my SSL certificate, but it is the TLS certificate now. So what is TLS? TLS is Transport Layer Security, which is used to provide authentication and encryption for HTTP. Now, a lot of people think that TLS is exclusively designed for HTTP, but it is not like that. So whenever you are talking about HTTPS, you are working with TLS behind the scenes always. TLS is the one that is providing encryption and authentication, but TLS is also used in other application layer protocols as well. I'm talking about the OSI layer. The application layer protocols such as SMTP, POP3, FTP Secure, they also use TLS behind the scenes for authentication and encryption. Now let's understand our example that you see on screen. So it is the same example that we saw here. It is just that we have elaborated the same. So what you see on screen is a user Seema. Seema is using Mozilla Firefox, and then here is pinkbank.com. Seema says, I want a secure connection. Are you really pinkbank.com? And pinkbank.com says, yes, I am. And here is my certificate. But from where did this certificate come? Now, certificates for popular websites that me and you access all the time, these certificates are usually signed and provided by certificate authorities. What are certificate authorities? Certificate authorities are the trusted authorities which signs your certificates, and these certificate authorities are trusted by all the popular browsers. So in our example, Pinkbank uses Let's Encrypt certificate authority. Now let's understand what is happening in this section. There is Pinkbank, and Pinkbank has generated a public key and a private key, and we have seen how you can generate public and private key in our previous section. So Pinkbank has a public and private key, and similarly Let's Encrypt certificate authority also has a public key and a private key. So what happens is Pinkbank says that I now want to use HTTPS, and whenever they decide that we want to use secure HTTP, it is then when they must reach out to a certificate authority so that that certificate authority can sign their certificate. And what is a certificate? What details are there in a certificate? Certificate holds your public key, when the certificate was issued, and when the certificate will expire, along with few more details. So if I go to, let's say, my Chrome browser and I go here, this is GitHub, I click here, I click connection is secure, and now I can check the validity of this certificate. If I click here, these are all the details that are present in your certificate. Here the certificate is issued by Sectigo and it is for github.com, and this is the date when it was issued, and this is the expiry date for the same. So you can check the certificate for any website that you are visiting using your browser itself. So let's go back here to our diagrams now, and Pinkbank decides, okay, I will create a certificate and I will have Let's Encrypt sign my certificate. So it creates a CSR. CSR is called certificate signing request. Let's Encrypt says, okay, let me validate whether you are the owner for pinkbank.com, because I don't want anyone walking to a certificate authority and telling that I own pinkbank.com's website. It doesn't work like that. For example, if I own amazon.com, then I should be able to prove it. And how that is proved is beyond the scope of this course. Just to give you a one-liner, you add certain information in your domain and that is how it is verified. So we'll see that maybe in the DNS section, but for now CA validates ownership of the domain and signs the certificate using its private key. And if you remember, in scenario 3, it is the private key that signed the challenge. So in scenario 4 as well, a private key is used to sign the certificate. And who is signing the certificate here? The certificate is being signed with the private key of the certificate authority. Now, certificate authority says, anyone with my public key can verify that I signed it. Here you remember, here the public key was here and public key verified that, oh yeah, this challenge is indeed signed by Seema's private key. So here anyone who has this public key can verify, oh yeah, this certificate was signed by Let's Encrypt certificate authority. And we'll see how this works. And if you have any confusions regarding this process, especially the certificate signing request and so on, in the next section where we discuss TLS in Kubernetes, we'll be dissecting this deeper. Now, in the second step, pinkbank.com says, yes, I am pinkbank.com. Here is my certificate, and we know what all details are there in the certificate. We just saw them, and this certificate is also signed by Let's Encrypt CA. And once the browser receives this, the browser says, yes, I can verify that you are indeed pinkbank.com and your certificate is signed by Let's Encrypt certificate authority. But Varun, how can the browser verify this public key, which can verify if a certificate is signed by the private key of Let's Encrypt CA, is not with you? How did you verify? A critical point here. The popular browsers already have the public key of all the popular certificate authorities. So popular certificate authorities like Let's Encrypt, Sectigo, VeriSign, Google certificate authority, AWS's certificate authority. So they already have the public key of all the popular certificate authorities. So whenever this certificate signed by Let's Encrypt CA is received by Seema's browser, the browser verifies that yes, this is signed by Let's Encrypt CA. So I trust that you are pinkbank.com. In the next step, Seema's browser says, I trust Let's Encrypt CA. Browser now creates a session key, a symmetric key, and encrypts it with the public key of pinkbank.com. And we know browser already has the public key of pinkbank.com. So what happens here now is, once the browser verifies that it is indeed pinkbank.com, browser generates a symmetric key. Understand, up till now we were only dealing with asymmetric encryption because we had two keys, public key and a private key. We were dealing with a key pair. But here the browser says, now that I have verified that you are indeed pinkbank.com because you have presented to me the correct certificate, I will now generate a session key and I will encrypt that session key with your public key, with pinkbank.com's public key. But Varun, how does the browser have pinkbank.com's public key? We understand that Let's Encrypt CA's public key is with the browser because browsers hold public keys of all the popular CAs. But how can the browser know the public key of pinkbank.com? It knows this because this information is there in the certificate that was signed by Let's Encrypt CA. And remember, this certificate belongs to pinkbank.com. It is the CA that just signed that certificate. So if I go to the browser again, you see that here is the public key for github.com. And here you have in this certificate the public key of pinkbank.com. And the browser encrypts this session key with the public key of pinkbank.com. And once this is encrypted with the public key of pinkbank.com, then it is only pinkbank.com that can decrypt it because it is pinkbank.com that has the private key associated with that public key. Only pinkbank.com with access to its private key can decrypt this session key. Both browser and server now share the same symmetric key. All data is encrypted using this key, fast and secure. Understand, in scenario 2, the problem was how do I share my symmetric key? Now, how do we share the symmetric key? We encrypt that symmetric key using the public key of pinkbank.com and we send that over the internet. And we can do that because now our session key is encrypted using the public key, and even if there is a hacker in my way, that hacker cannot decrypt it because the private key is only available with pinkbank.com. Now once this session key is shared with pinkbank.com, then only these two entities in the entire internet know about that session key. And that session key can now be used to encrypt and decrypt data. That is how TLS works. Extremely simple. Once you understand the foundations, Kubernetes security will be a cakewalk for you. So what is HTTPS? HTTPS is encryption in transit plus authentication via TLS certificates. That is what we saw. We saw how asymmetric encryption and symmetric encryption joined their hands to facilitate secure communication between two remote systems. I hope all these concepts are now clear. That concludes our lesson on encryption and TLS. We have covered the basics of encryption, both symmetric and asymmetric, and explored the inner workings of TLS, which plays a pivotal role in securing communication between different systems. In the next session, we will build on this knowledge and explore how TLS is applied within Kubernetes environments to secure communication between Kubernetes components. If you have any questions, feel free to ask them in the comments section and I will reply. This helped. Do consider liking, sharing and subscribing. It will mean a lot to me. Thank you very much.